opposite side of the equilibrium, right? That's number one. Number second, your conjugate base should be basic in nature, right? So in the reverse reaction, you have acetate ions which will accept proton from hydronium ion. So acetate ions are acting as the base, right? So I will put here base, and the conjugate acid for water will be hydronium ion. So now we got conjugate acid base pairs. That's what we have studied before. On the reactant and on the product side. Now, given that acetic acid does not want to go on the right side, that means it does not want to form acetate and hydronium ion. What does it tell you about the acetate ions? What does it tell you about the basicity of acetate ions? Is it a strong base or a weaker base compared to water? Because we have base on both the sides. What do you think now? So think it in this way. The forward traffic is not much. The reverse traffic is a lot. That means this is more basic compared to water, right? Because water is accepting proton from acetic acid, right? But then it is not doing it effectively. It is not doing it efficiently. That's why on the right side, you have less amount of acetate ion and hydronium ion. By that analogy, we can say that the reverse traffic, that means the acetate ion want to go towards the left side. That means acetate ions are stronger base than water. So it tells you that when you put acetic acid, weak acid in water, it's going to generate a stronger conjugate base. When you add, let me put it here. Let me put a strong acid in water. What this acid wants to do is completely dissociate into ions. So the forward equilibrium is more than the reverse equilibrium. So in the forward equilibrium, I'm getting Cl minus and again hydronium ion. So hydrochloric acid is a strong acid. That means Cl minus is a weak base because it does not want to accept proton from hydronium ion to reform HCl. Because look at the equilibrium. It's the traffic which is towards the product side. It is more compared to the reverse side, right? So understand this basic concept. Let's expand this one into the next part. Now, suppose if I take acetate ions, simple, right? If I take salt of it, right? Because we can, just like NaCl, right? You put HCl and mix it with NaOH, you get NaCl and water. Now, the forward reaction is way more predominant than the reverse reaction. It's like this, right? But see, this is the salt. This is a salt of your strong, the weak base. And what do you think about this? A weak acid. Na plus is a weak acid, right? So let's think in that same manner, just like your sodium chloride, you have sodium acetate. What happens if you put this in water? Well, we just spoke about it. We just said that acetate ions are basic, more basic than water. What will happen in that situation? Acetate ions will start to accept protons from water because now water will start to act like an acid in presence of acetate ions. I can have another equilibrium here. And I can have plus NaOH. See, this time I am generating hydroxide ion. So by putting acetate ions in water, you may be generating hydroxide ion. This process is called salt hydrolysis. So far, so good. Did you go through this in your lecture, the one that we had on the videos?
Yes.
Okay. Now, here's something interesting that I'm going to do. This time, I'm going to add an acetic acid, and I'm going to add its salt. Let me put it here. So these were two independent reactions. Now let's see what happens if I have a weak acid and I put sodium hydroxide, which is a strong base, and I mix them together. Now we know acid reacts with a base to give you salt and water. Well, let's see what happens. So the first thing that you're going to generate is salt and water. This was supposed to happen, right? Okay. Interesting thing is that your salt and water can react back to give you your acetic acid. That's the nature of this reaction, right? Now, my question is, based on Le Chatelier's principle, what you have studied so far, if I add acetate ions from outside, what would be the effect on equilibrium? Suppose this reaction has attained equilibrium. The number of molecules of acetic acid reacting with NaOH is the same as the number of molecules reacting between sodium acetate and water. So forward reaction and reverse reaction are now equal. You have established an equilibrium. At that equilibrium, you are adding acetate ions from outside. What would be the impact?
Would it become more basic?
Would it become more basic? Okay, but that way we are referring to acidity and basicity. But then where will be equilibrium shifted? On what direction will it be shifted?
The reverse?
Absolutely. Very good. Very good. So when I add from outside, when I add acetate ion, my equilibrium will be shifted to the left side, which is the reactant side. So I'm going to generate more acetic acid, undissociated acetic acid in my solution, right? Okay. Now, when I add acetic acid extra from outside, my reaction will be shifted to the right side. Okay. Now, this effect by adding the ion, the common ion from outside, we call it a common ion effect. Common ion effect. So as I said, you add acetate ion from outside and the reaction will be shifted to the left side. Now, let me give you one interesting situation. The same reaction, acetic acid, sodium hydroxide at equilibrium gives you sodium acetate plus water. Now, suppose instead of adding sodium acetate, how about I add potassium acetate? See, it looks so strange, right? Cook. It's not cook, actually COOK. So if I add potassium acetate in this equilibrium from outside, what would happen? Think about it. Any guess?
Will it form more acid and another base?
Okay, that's true. Very good. So when I add this from outside, we have to look for the common ion on the right side. So the common ion I can see acetate ions. So these are the ones which are actually reacting with water. Sodium and potassium are just simple spectator ions. They don't take part in the reaction, right? So acetate ions are the common ions and they drive the equilibrium to the left side. So it doesn't matter where this common ion is actually coming from. As long as it is common between what you have at equilibrium and what you're adding, it's going to change the direction of equilibrium. And that's why the effect, we call it a common ion effect, right? Okay, so keep in mind, irrespective of the source, where it's coming from, it will shift the equilibrium to the opposite end. Now, suppose I take the same reaction at equilibrium. Now, this time I'm adding, suppose, let's put it as magnesium hydroxide. What would be the effect on equilibrium in this case? Would it be on left? Would it be on right? What would happen in that case? Shifts to the right side. Absolutely. Very good, Abram. So equilibrium will be shifting to the right side. Now, let us see if we want to calculate a pH of a solution where I keep on manipulating those things by keep on adding the common ion on one side, on the other side, and see what is the change in the pH, right? Let's see what happens with that. But then before that, I need to have an equation, right? And that equation we are going to derive, we call it Henderson's equation or Henderson-Hasselbalch equation. Okay, so suppose if I'm dealing with a weak acid, now guys, keep in mind, Henderson-Hasselbalch equation is for weak acid only. So suppose the generic equation, the generic acid is HA or weak acid. You put it in water and it will partially dissociate into hydronium ion and the counter A minus ions. Right? Now, if I write down in this equation, if I write down Ka, that would be equals to hydronium ion A minus divided by HA. Now I know that we have derived the same equation before. I'm doing it one more time, right? But then this is going to be related to this chapter. Okay. Now, what I can do in this case, I can separate hydronium ion and the rest of the terms separate, right? Okay. So I can write it as hydronium ion multiplied by A minus divided by HA. It's one and the same thing. I simply took out that term separately, but then they are still multiplied because there is one below hydronium ion, right? So we can think in that way. The next thing I'm going to do, let me make it bigger so you can follow what I'm writing on the previous slide. Okay. The next thing I'm going to do is I'm going to take the log on both the sides. Okay. So log Ka equals to log hydronium ion. And this multiplication sign between the two terms will become now addition because you're taking log. Well, now I'm going to take the negative sign on both the sides. I'm going to multiply both the sides of this equation by -1. So that way now I got negative log Ka equals to negative log hydronium ion minus log A minus divided by HA. Makes sense. Looks simple. But then negative log Ka is pKa. Negative log of hydronium ion is pH. Negative log of A minus over HA. But see, here we are trying to find pH. So we need to rearrange this equation. So what I'm going to do is I'm going to take the term which is here on the left side, right? So when I do that, my negative becomes positive. So my pKa plus log of A minus divided by HA, that is equals to pH. In other words, if I just want to make this equation look simple, I will write pH equals to pKa plus log A minus divided by HA. Now, did you see something interesting happening here? Your pH depends on the strength of the weak acid that you are using, number one. It depends on the strength, it depends on the concentration of the conjugate base, which came out of that acid. But then it does not say where this A minus came from, right? It can come from any other source. As long as you know the concentration of A minus, irrespective of the source, you can plug in that value here. And HA is basically undissociated acid at equilibrium. Now, this equation is a classic Henderson-Hasselbalch equation. Let's solve one problem on this one. Give me a second. So I will copy one problem and we are going to do it. So see, nitrous acid is a weak acid, right? So we can use Henderson-Hasselbalch equation for this. And I will make it a little bit bigger so we can read it clearly. So we need to find H plus ion concentration in solution, which is 1 molar in nitrous acid. So I'll just make it like good. Give me a second. Oh, where can I find that? Oh, it's not there. I will simply use this. Okay. Okay, so we are given Ka for nitrous acid. How should I approach this problem? Any guess, guys? Now see what is given to us. We have been provided the concentration of nitrous acid, which is 1 molar. We have been provided concentration of its salt, which is the salt of a weak acid. That's been provided to us, which is 0.225 molar. We have been provided Ka for nitrous acid. Now, when you look at this equation, pKa plus log salt concentration divided by undissociated acid concentration. I'm just going to write it in a simpler form like this. A minus is a salt and HA is an acid, undissociated acid. So that's what we have here, right? So do we have the salt concentration? Yes. Do we have acid concentration? Yes. Do we have pKa? Well, you need to find pKa from Ka. So we have that. Can we find pH? Guys, I'll give you 2 minutes to do that. Find me pH of the solution and write down in the chat box, send the direct message to me. Do not write in the group chat. Did you guys get the answer so far? I think I saw
I'm
one.
still trying.
Okay. I did see one answer on the chat. So, Roberto, can you find the hydronium ion? You got the pH correct. What do you do after that? So let's start with the pKa, right? We need to find this value. Now, how do we do that? pKa equals to negative log Ka. That's going to be negative log 5.6 10 to the power negative 4. So should turn out to be 3.25. How many of you are getting 3.25?
Yes, got that part.
Okay, so that one is there. Now let's try to plug in the values for the acid and the base concentration. So pH equals to 3.25, the one that we calculated, plus log. The salt concentration, we already know 0.225 divided by the acid concentration, which is 1.0. So when you do the math, what would you get? So 3.25 minus what would be the value? So if you take the log of 0.225, that's going to be 0.65. So 3.25 minus 0.6478. So you can simply say 0.65. That's going to be the answer for the pH. And this will turn out to be 2.6. So now you got the value for pH, which is good. But then what exactly is pH? pH equals to negative log hydronium ion concentration, right? Now, how do I go about this one? Well, I will go on to the next slide. I'll just make it a little bit bigger so you can follow what I have on the previous slide. So 2.6 is the value for pH. That's going to be equals to negative log hydronium ion concentration. I take the negative sign on the other end. So that's going to be negative 2.6 was to log hydronium ion concentration. Now this is log to the base 10. So I can simply rewrite this equation as hydronium ion equals to 10 to the power negative 2.6. That's what we have. So can you calculate the value for this one now? Are you guys getting answer 2.5, 10 to the power negative 3? Let me see what we have. This is the concentration of hydronium ion. So if you are given those two values, you can find pH. And if you can find pH, you can find the hydronium ion concentration. So guys, what I would recommend is taking the screenshots. Keep on taking the screenshots so you have all the material that I'm doing in the class as well, right? So you can always do that. Let me tell you that. So far, so good. Any doubts so far?
Professor, why do you put a 10 under the log? Is that to get rid of it?
No, basically when we don't write, it's already there. So there's a difference between the natural log, which is equals to log to the base E. And if I simply write log like this, it is actually log to the base 10. So just to show you where this 10 came from, it came from here. So if I take it on opposite end, this is how it's going to look like. I need to raise that value to the power of 10.
So you're dividing off the log?
No, I'm not dividing anything here. I'm just simply taking the log on, I'm just removing the log. In a sense, I'm taking an anti-log. Think in that way.
Okay.
All of us on the same page so far on this, guys? Now,
A little iffy still, but I'll need more practice.
okay, so we'll solve some more problems. So let's go on to the next one, right? Now, suppose here in this case, you are only given the concentration of, if you're just simply given the concentration of acid, right? Initial concentration of acid. And let's try to build it using the ICE table, right? So let me put an example. See, here in this case, you were already provided. You were given the concentration of base, you were given concentration of acid. Quite simple to plug in the values and get to the equation. But suppose if you are not given something like this, suppose you are given an equilibrium of acetic acid, again a weak acid, giving you acetate ions and hydronium ions. Suppose this is the equilibrium that's been provided to you. And the next thing is, if I provide you the pKa for acetic acid, and that's 4.78. So where should I write it? I'll just write it here, pKa 4.78. This is provided to you. Okay. Let's think that if we start with, I'll just give any number. Let's start with the initial concentration of acetic acid. What do you want? I mean, just give me a number less than 1 molar. How much? What would be the concentration that you want to work with? You take that concentration of acetic acid and put it in water. Let's see what we have. Well, Abraham says 0.75. We are going to take 0.75. So suppose we start with the initial concentration 0.75 molar, and I put it in water, right? My acid is now going to dissociate. But then initially, it is simply undissociated acid. So there is no acetate ion, there is no hydronium ion, right? Okay. At equilibrium, suppose I form X amount of acetate ion and I form X amount of hydronium ion. What was the change? I added X amount in the system. I added X amount of hydronium ion in the system. That means I removed X amount from my undissociated acid to get to that X amount. So what is remaining of acetic acid? Well, it's 0.75 minus X. So far, so good. Are we on the same page so far on this?
Yes.
Okay. Now let's make the things a little interesting because we have done this before, right? We have made the ice table. Now at this equilibrium, let me add. Okay, give me some number. Again, less than 1 molar. Give me a number of acetate ion concentration, which I'm about to add from outside. Suppose if I'm adding, let me put it as the common ion, I'm adding it from outside. What amount do you want to add? Well, okay, Abram, we will add 0.25 molar. Very good. Oh, that's great, actually. I got the two students giving me the exact same concentration, 0.25 molar. Very good. Okay, so now I'm adding from outside in this equilibrium, 0.25 molar acetate ions. Can you tell me how should my ice table, the new ice table, look like? So I'm just going to say E modified, right? I'll just write the whole term so that you're not confused. So now my E modified, how should that look like? Any guess on that? Because I'm adding it from outside, right? Okay. Let me make the things quite simple. Here, I'm adding extra amount of this one. So I'm adding acetate ions. Am I adding hydronium ions? No. So that stays same. So I'm just going to write in another color. So X stays same when I'm, for hydronium ion, it stays same because I'm only affecting acetate ions. I'm only increasing the concentration of acetate ions. Okay, so that stays same. What happens to the total concentration of acetate ion? Well, you just added 0.25 molar plus X. Well, that's going to be the concentration of acetate ions, right? Okay, now what happens on the right side? See, it depends on how much hydronium ion do I have to react with acetate ion. No matter how high amount I have for acetate ions, as long as I don't have hydronium ion enough, I cannot revert the equilibrium to the left side. Okay, so this X stays the same because this one depends on the hydronium ion, does not depend on your base, extra amount of base that you added. So this stays same. Well, I got a new equation. Now I'm going to use Ka on this equation. I'm going to expand it a little bit so you can see. Now Ka, that's going to be the acetate ion concentration, hydronium ion concentration, divided by, if I just go back, that's going to be acetic acid ion concentration. Acetic acid concentration. Now, if I simply plug in those values, the one that I have, so 0.25 plus X, this is for acetate ions. Hydronium ion did not change, divided by 0.75 minus X. So far, so good.
Yes.
Okay. Now, let's go on the next slide. So now we got this one. Am I given Ka in for this equation? Answer is yes. It is given indirectly. How? My pKa is 4.78. Therefore, my Ka is 1.8, roughly 10 to the power -5. All of you can check it. Is it -5 or -4? Let me see what we have on the chat box. Can you confirm that what I have is right? Is it 10 to the power -5 or -4? Okay, 1.7 10 to the power -5. So I'll just take that one. I'll just use what you guys have. I'll take 1.7 10 to the power -5. So we have how would I get it off the top of your head? Okay, now you need to solve this one. So since I've been doing this for last 30 years, I know the value. I can simply look at the value. So 4.78 is roughly 5. So I'm looking at negative exponent 5. And 4.78 is not exactly equal to 5. That's why we got 1.7. So that's how I did my math, right? So I was off by a little more. I mean, like little, but then I've been doing these kind of math and calculus a lot. So I can, roughly figure out how that value would look like. So I'm just answering a question on the chat. Okay, so Ka, I got it. Okay, so I'm just going to write that value 1.7 10 to the power -5. That's going to be equals to, now I can expand what I have in the numerator on the right side. So I can say x squared plus 0.25 x divided by, now 0.75 minus x. Now, in a way, there are two things which I can actually assume in this case. Now, can you tell me what would be those things? I can make some assumptions over here. Any idea what those assumptions would look like? X in the denominator is negligible, absolutely. So I can think of that, yes. So in a way, I can simply ignore X because X is too small. So I can think 0.75 is way bigger than X. So I can simply ignore that. So I'm going to write here 0.75, way greater than X. So ignore X. So when I say ignore X, you are ignoring X in the denominator because that's where we are comparing. So I can say 1.7 10 to the power -5. That's going to be equals to X squared 0.25 X divided by 0.75. Can I rearrange this equation? Absolutely. What do I do next? Any guess? Can I make one more assumption here? Now let me ask you a question. when you are squaring a small number, will that number become small or big? When you're squaring a small number. Exactly. Very good. Guys, you guys are getting really good at math, in fact. Yeah. So suppose I'll just give you an example so that you can see it. It's for everyone else as well, right? So if I square 10 to the power -2, that's going to be 10 to the power -4. If I square 10 to the power -5, that's going to be 10 to the power -10, right? So when you square a small number, it becomes way smaller than that. Well, isn't it that we just said that your acid is a weak acid? It's a very, very weak acid. So squaring a number, that means squaring this x is already small number, right? So I can simply ignore that, right? So now my new equation from this one will be 1.7 10 to the power -5. That's going to be equals to 0.25 multiplied by x divided by 0.75. Well, we got something here. We were able to ignore x from the numerator, right? Because x squared was so small, we can simply ignore x squared compared to 0.25x. Can you give me the value? (5.1 10 to the power -5). Yes, Roberto, you're right. So 5.1 10 to the power -5, because that's what I'm getting as well. Because I'm solving it with you guys, because you gave me those numbers, so I'm solving it along with you. So we got the value of x here. Well, what do we do next? Look what x corresponds to. X corresponds to the amount of hydronium ion as well, right? Okay, so let's see what happens with this one. So pH equals to negative log hydronium ion. That's going to be negative log 5.1 10 to the power -5. Can you tell me what would be the pH now? Four 4.3. That's right. That's what I'm getting. I'm getting 4.29. So we are getting 4.3. See here, we added acetate ions from a different source into the solution. And that's what exactly I'm getting, right? Now, what if I'm not adding that? What if it was not there? What happens in that situation, right? Let's look at the pH in that situation as well, right? So I'm going to use the same values the way we had it here. But suppose if I'm not adding this one from outside, so there is no 0.25 plus x in the solution. Whatever I have is my first equilibrium. So I'm going to write it exactly as it is. So let me go back. My Ka will be acetate ion concentration, hydronium ion concentration, and undissociated acid. Again, in this case, I'm going to follow the same principle. Your Ka was 1.7, 10 to the power negative 5. Acetate ion concentration here in this case is X because we have not added from external source. Again, in this case, it's going to be X. On the bottom, it's going to be 0.75 minus X. Now, if I solve this one, just the way we did before. Okay, so that way, now I'm getting the value. If I just simply think that 0.75 is way too bigger than X, so I can ignore it. I can ignore it in the denominator. So I'm going to write here 1.75 or 1.7 10 to the power negative 5. That's going to be X squared divided by 0.75 because I simply ignored X. Subtracting a very, very tiny number from 0.75, which is a big number compared to that, will not make a big difference in 0.75. Now you would wonder, can we ignore X squared in this equation? Answer is no. Do you know why is that? Because here, see, when we ignored in the previous example, we were comparing X squared compared to 0.25X. See, this number is way bigger than X squared. So we were able to ignore it. Now we cannot do that, right? Because if you simply ignore, we don't have any variable left on, say, square x 7 to the power negative 5 multiplied by 0.7. Find me the value of X. Guys,
Professor, you're cutting in and out. Like we hear some of your
Okay.
words, others we
okay, now you can hear me, right? No?
yes.
Okay. So here we cannot ignore X squared because we were comparing X squared with 0.25X. So 0.25X was a big number compared to X squared. So we were able to ignore it. In this case, we cannot ignore it because the moment you ignore it, you have a number in the numerator, which is 1. If you ignore X squared, 1 will be left. You have a number in the denominator. You have the number on the left side. You just have the numbers. You don't have any variables left. So do not ignore X squared in this case. Okay. Now, can you find me X in this one? (3.6 10 to the power negative 3). Okay, let me do it because I'm doing it for the first time, this problem, because you gave me those numbers, 0.75. So I need to verify it. So you are taking square root of 0.001275. Let me take. Guys, why am I getting 3.5, 3.6
I'm
10 to
probably
the
wrong.
power? I'm sorry?
I said I'm probably wrong.
I'm getting 3.6 10 to the power negative 2. Are you guys getting that? Let me check one more time. Maybe I'm doing something not right with my exponents. So I got that, and then I multiplied that with exponent 5 minus. Yes, I'm getting the same answer as you guys. I'm getting 3.6 10 to the power negative 3. Yes. Okay, guys. So X is 3.6 10 to the power negative 3. Well, this one is the hydronium ion concentration. So plug in this value in the pH equation. Can you tell me the pH now? And you'll be surprised. You'll be really surprised by that. 2.44. That looks correct to me, Roberto. Now, did you see something, guys, really interesting here? Here, I simply added the salt in my equilibrium. Added simple salt. I did not add anything else. I simply added salt. And my pH went from 2.44. So this is pH before adding 0.25 molar potassium acetate. This is pH after adding 0.25 molar acetate, potassium acetate. You can see just by adding the salt, you are changing the pH. In fact, you are making the solution less basic. Now try adding the Cl minus base in your hydrochloric acid reaction. It's not going to change the pH because it's a strong acid. Cl minus is a weak base. Okay, so this is also called the salt hydrolysis or the common ion effect. That's what you are seeing here. Okay, any doubts so far before I go to the next topic?
Yeah, Professor.
Mhm.
Getting from pKa to Ka, can you just go?
Okay, so if your Ka, or from pKa to Ka, okay, pKa is negative log to the base 10 Ka, right? If I write your pKa is 4.78, that's going to be negative log to the base 10 Ka. So just like what I did with the pH and hydronium ion, I can say 10 to the power negative 4.78 equals to Ka. If you solve this one, you're going to get the answer 1.7 10 to the power negative 5. That's going to be equals to Ka. Okay. So,
Thanks, I needed that too.
oh, okay, good. Okay. Now, let's think about what if I'm given the mixture of the weak acid and its salt, right? Let's see what happens. So I'm going to put one diagram. This is taken from your book directly. So you should have access to that one as well. Now this is happen if I add external H plus in solution. So when you add H plus, well, we know salt of weak acid is a strong base. The moment you add H plus in the solution, your fluoride ion simply going to bond. When it does that, it's going to form undissociated HF. So now your new mixture will have more HF and less of fluoride ion. Is it going to make a big difference in pH? Answer is no. Why? Because HF is a weak acid, does not want to give out H plus ions. So what you did was you removed H plus ions from the solution and you made a weak acid out of it. On the other hand, when you add base into this solution, your weak acid is going to react with HF. Next, you're going to increase the concentration of fluoride ion, decrease the concentration of HF. Is it going to make a difference in pH? Answer is no, because compared to fluoride ions, hydroxide ions are really strong base. So you replace strong base by a weak base. Here, you replace strong acid by weak acid. Now, how does it play into the pH of the solution? Well, when you do that, when you start with a mixture like this one, you are not going to change the pH of the solution much. And these solutions are called buffer solutions, right? Okay, so what are buffer solution? They are the salt. I mean, they're mixture. I'll just put it here. Of weak acid plus their salt. Or it is also a mixture of weak base plus their salt. I will give you a few examples over here. Guys, can you hear me?
Yes.
Guys, okay. Looks like my internet connection is not stable today. I'm not sure why it's that. So we were discussing about this one. Okay, so we were discussing about the weak acid and its salt. So these are all buffer solutions on the left. On the right side, we have ammonia and ammonium chloride. It's the weak base and its salt. It's a buffer solution, right? So you can simply spot the buffer solution just by looking at whether you are dealing with a weak acid or whether you are looking at a strong acid. For example, I'll just give you one more example. Hydrocyanic acid is a weak acid, and the salt of hydrocyanic acid is sodium cyanide. Again, this is a buffer solution, right? Okay. The next thing we will be discussing is if you want to calculate the pH of a buffer solution, right? So let's take the example of hydrofluoric acid, and we will start from there, right? Okay. So I'll give you two solutions, and let's see what happens with that. Okay, give me a second. So, and that will involve Henderson-Hasselbalch equation. Now, before we stop this one, is this, so we have NaOH and NaCl. Is this a buffer? And also tell me about HCl, which is acid, and NaCl is its salt. Are these two buffers? I'll give you a minute to think about it. Anyone? You have two solutions. One is HCl with NaCl. The second one is NaOH and NaCl. Tell me whether these two are buffer solutions. Write down in the chat box. I want everyone to respond. So the question is whether NaOH and NaCl, the mixture, is it a buffer solution? And also whether HCl and NaOH, HCl and NaCl mixture, is it a buffer solution? See, the primary requirement for it to be a buffer, we should have a weak acid and its salt. Sodium hydroxide is a strong base. HCl is a strong acid, so it does not meet the requirement for a buffer. Okay, now given that, let's jump into the next aspect. Yes, so let's jump into the next aspect. Let's solve one problem. Now we need to find, now since as I said that if you have a buffer solution, the pH is not going to change when you add external acid. Let's verify. I mean, it's not going to change to most extent. I mean, but then at a certain limit, once you run out of the stock solution, that means, let me put it here. Say, for example, you keep on adding H plus and you keep on decreasing the value of fluoride minus. At certain point, you will run out of fluoride ion. And that's when your buffer will not act like a buffer anymore. When you add more H plus, you are going to increase, you are going to decrease the pH. That's going to be a problem. In the same way, you keep on adding NaOH and you will keep on removing hydrofluoric acid from the solution. And at a certain point, you will completely take out all your weak acid. Now, when you add OH minus, your pH is going to rise drastically. So it depends on your mixture of HF or weak acid and salt. The moment you run out of one component, your mixture stops behaving like a buffer, right? So there is a limit to the buffer solution. We call it buffer capacity. But let's solve this problem. So we want to find the pH of buffer solution of a buffer, which is 0.5 moles acetic acid and 0.5 moles acetate, and you are given the total volume of 5 liters. Keep in mind, we will calculate it before adding HCl and after adding HCl, and we will see the change. Okay, so first find me before adding HCl. I'm going to use this equation, pH equals to pKa plus log salt concentration divided by undissociated acid. Are you given pKa? Yes, I will give you the value right away. It's the same acid that we're using, 4.78. Are you given A minus before you added HCl? Yes, you are given acetate 0.5. You are given acetic acid 0.5. Can you find me the pH now? But guys, be careful. It's not 0.5 and 0.5. Let me show you something here. This should ring a bell. What is the concentration of now acid. It's 0.5 moles in 5 liters. So you should know what is the molarity, because that's what you are putting it here, not the exact number of moles. You're going to put molarity. Very good, Roberto. Very good. So number of moles divided by the total volume will be molarity. So 0.5 divided by 5 liters is 0.1 molar solution. So your pH will be 4.78 plus log 0.1 molar of acetate, 0.1 molar for undissociated acid at equilibrium. So this turns out to be log of 1. That's going to be 0. Well, we got pH equals to 4.78. This is our starting pH of the buffer. See, this is also the ideal pH of the buffer. The moment you see pH equals to pKa, that's the ideal buffer, because you have equal amount of weak acid and its salt. Perfect buffer to work with. Okay, now you are adding 0.35 moles of HCl into this solution. You're adding the strong acid into this solution. So how should I approach this? Write down step number 1, write down the equilibrium. This should give you acetate ions plus hydronium ions. Follow the same principle that we use for the common ion effect. Here, the common ion that you're adding is H plus ions. So I'm going to build the ICE table. Initial, change, and at equilibrium, right? So what is initial? What we started with? Well, 0.1. Do we have anything for acetate ion when we started? Yes, we had that one, 0.1, right? Because that was the mixture given to us for the buffer, right? Now, can you tell me how much hydronium ion do I have at equilibrium? Any guess on that? Think about it. This one will dissociate into X. So this one is supposed to be X plus X, the way we did it for the common ion. You remember that one? It's exactly the same. This one, we are adding it from the external source because we are already given that. See, we are already given acetate ions. We are already given these. We are given the mixture of that. So this is what we have, right? This one will be given to us. Okay. What happens when I have modified? So I'm just going to write the modified equilibrium. Can you tell me what would the modified equilibrium look like? So let me make it more palatable. So this is initial, we didn't have that. If we have X, 0.1 plus X, this is going to be, I will just say negative X. That's how it's going to be. And E modified, I'm going to write the same thing here. So 0.1 plus X, X, and this is 0.1 minus X. This is the previous equilibrium, and I'm going to add now. This is E. Now, at equilibrium, I'm adding hydronium ion, which is 0.35. This stays the same, but now this changes to X plus 0.350, because we are adding this amount, right? You can see that. Is it the number right? Or did I make any mistake? You have to be prompt. I'm adding 0.35 moles, but then that too is in 5 liters. So how this one should look like, guys? What should be the molarity? I've used moles over here. This is wrong. Correct me, guys. What should be the molarity? of external acid that I'm adding. Very good, 0.07, absolutely. So now the molarity that I should be adding into the system is 0.07. Okay, write down the Ka equation for this using this one. So Ka equals to your products, which is 0.1 plus X, and X plus 0.07. This is your hydronium ion divided by 0.1 minus X. Can you solve this one, guys? Can you expand it the way we did it earlier? So you have X squared. I'm simply going to write the way it is. Divided by 0.1 minus X. Now, can we make some assumptions over here? Guys, can we make some assumptions over here? So the way we did it earlier, we are going to do the same assumptions. X squared is too small. We can ignore it. And then here, this is 0.17x plus 0.007. And we can ignore X compared to 0.1. I'm going to say 0.1. And Ka in this case is your 1.7 10 to the power negative 5, right? If I simply expand it, that's going to be 1.7 10 to the power negative 5 multiplied by 0.1. That's going to be equals to 0.17 X plus 0.007. Okay, guys, what next? I can still simplify this one. 1.7 10 to the power negative 6, because if you multiply this with 0.1, this becomes 10 to the power negative 6. That one will be 0.17x plus 0.007. Well, what do you guys think? Because I see a big problem here. Do you guys see the big problem? I can see a huge problem. Do you guys see that problem? How many of you see that problem, guys? Exactly. Can we have X equals to negative? No, we cannot have a negative concentration. Either you have something or you don't have something. You don't have anything, right? You cannot have negative or something. So can you find the mistake? Where is the mistake? There is a mistake. I can see it right there. Can you spot that mistake? Think about it, guys. Because I can see it right there. One of the assumptions and one of the equations. I will give you the hint over there. If you think there is a problem with assumption, tell me what is that. Anyone, guys? This is the time. Think about what was the buffer solution. What was the buffer solution? In buffer solution, if you add external acid, what happens to that acid? Think about it. I just wrote it down. I'll just move it back a little bit. Here I mentioned, if you put acid in the solution, your salt is going to react with this acid, isn't it? So you are decreasing the amount of H plus from the solution. Now look at this assumption. See what we have done. You are adding this extra amount from outside. What should happen to this amount? You are adding it from outside. So at equilibrium, this will be taken out. Neutralize, absolutely. So you should be removing this amount of X from your solution. Well, there was a problem here because you are taking it out. So this one should have been negative. You are removing it. In that way, since you are adding acid, see, I'll just go back. See, now you added more acid in the solution that you started with. So you are adding that amount. Well. So this should have been positive. Well, go back to the equation. Look where we did that mistake. Do you see that mistake now? This one should have been negative. This one should have been positive. See how assumptions, every mathematical thing is connected with a concept. That's why when I started today, I told you everything is interconnected. You make a problem with an assumption, you do the problem with a math, and you end up with something which is out of this world, right? So if you change this one to negative sign now, if you change this one to the positive sign now, which makes sense. But again, at the bottom, we are making an assumption, so we can get rid of that. But can you write down the correct equation over here now? What will be the correct equation? Write it down. Let's see if you guys can do that. X squared stays the same. Then what happens? You have 0.1 X stays the same. Negative 0.07 X. Negative 0.07. 0.007, I'm sorry. Can you now solve it for me? That way, now this value will change. Can you write down for me, guys? Because now I'm going to assume that X squared is too small. I can ignore it. Now, can you do it for me, guys? Can you tell what you're getting? See on the top, are you guys getting 0.03x? Very good, see? And then 0.007. Okay, so now we are correcting everything, right? So this stays same, but now this one changes. Well. Let's see what we got here. 0.03x minus 0.007. Now, does it make sense? Did you notice I mentioned there was a problem with assumption, there was a problem with the equation. Now you saw how it flows, right? Okay, so I can say 0.03x equals to 1.7 10 to the power negative 6 plus 0.007. Can you find me this number now? Can you find me x? I think from here is going to be quite simple for you. So when you say 0.23, how did you get to that number, Roberto? Point 0.23. Okay, I think you are right. 0.23 looks right to me. So X in this case, 0.23. Well, I agree with that one, right? Now, this happens. Yeah, that's right. Okay, good, very good. So now you found X, right? Now, what do you do with X? What exactly is X? X is basically your hydronium ion concentration, right? That was supposed to be your X to begin with. What do you do after that? You found X. What do you do next? Still, we got some problem here with this equation. Okay. So you guys are getting good at it. I can see that. Okay. So now the next thing that you're going to do is find the concentration of acetic acid, find the concentration of acetate ions based on the X. Now, go back to the modified equilibrium. Look at the concentration of acetate ion, 0.1 plus X. The same thing happens with your acetic acid concentration. It's 0.1 plus X. It's the same thing, but then this X is coming from where? Can you solve it for me, guys? And also, do you see any problem with another assumption here? Let's see if you can figure that out. It's right there in your plain sight. I'll give you 2 minutes because on the 3rd minute, I will solve it by myself. There is one more problem, guys. Let me put it back here. Let me put it back here. There is one more problem with that assumption. I gave you the hint right there. Right here, I gave you that hint. Do you see what is the problem? Look at what is happening. When you add H plus, can you tell me what happens to fluoride ion concentration? It is decreasing, see? So what should happen over here, guys? What should happen here? Should it be plus X or minus X? Absolutely, very good. So now you give me the concentration of acetic acid and acetate. So I'll just give you acetic acid. You have 0.1 plus 0.23. And your acetate ions, which you just lost, 0.1 minus 0.23. Well, we got a problem one more time. Did you just see what happened here?
Wouldn't we have to correct the concentration of like acetate ion on the previous, like when we found X?
Yes, exactly. So what was wrong over here? Are we missing one term? Okay. See, in the forward reaction, acetate ions are generating acetic acid is generating acetate. So far, so good. So based on this ICE table, this is correct, right? So you have 0.1 minus X, you're going to get X from this equilibrium, plus X is hydronium ion is coming from that equilibrium. But when you add external hydronium ion, there should be this one term as well. So you are generating X from acetic acid, but then you are also removing 0.07 by reacting with hydronium ion. So that should be taken out from this equation. That's the problem here. Does it make sense now?
No, I'm totally lost.
Okay. You have two equilibriums happening at the same time. You have acetic acid independently giving acetate ion and hydronium ion. So far, so good. So before you add external acid, this is what is happening. So you start with 0.1. Just if acetic acid was dissociating, you will be taking out negative X from acetic acid. You will be generating X amount of acetate ion and X amount of hydronium ion. But acetate ions were already present in your solution. How much? 0.1. So total amount was supposed to be that, right? This was the buffer solution, right? Okay, so your equilibrium for the buffer solution will look like this one. 0.1 minus X, 0.1 plus X, because you had already 0.1 molar in your solution. And this X came from the dissociation of your weak acid. But now there's a modified equilibrium because you're adding from outside hydronium ion. How much you are adding? 0.07 molar. So when you add that, it will take out acetate ion. So you should be removing acetate ions. But then acetate ions are coming from two sources. One, which was externally added in the buffer, acetate ions. And the second, they are coming from acetic acid, the dissociation of acetic acid. So these two are the sources where we are getting it from. But then we are also removing it from the solution by adding external H plus ion. How many of them are we removing? We are removing 0.07. So now we got three terms over here to remove acetate ions. So my net concentration will depend on acetate ion coming from acetic acid, acetate ions that were already present over there as a buffer. So because the buffer is a mixture of the two components. So that's the second source, but I am taking it out when I'm adding external acid, HCl, from outside. That's why I have term number one, I have term number second, and the term number three. This is going to give me the exact amount of acetate ions in the solution. And now when I'm adding hydronium ion, I'm diverting my equilibrium to the left. So I'm generating my acid instead of removing it. That's what I'm doing right now, right? Let me go back. See, I'm generating acid, undissociated acid. It is more than what I started with. So I should be adding that amount. But then where is that amount coming from? It is coming from hydronium ion reacting with the net amount of acetate ion remaining. That's where it is coming from. So acetate ions are decreasing, undissociated acid is increasing. That is where we are. So what we are going to do, we will be solving this problem one more time on Tuesday. Guys, come prepared with this problem. We'll be solving it one more time. But I want you to be with me because the problems like these will be everywhere. I'll tell you that, right? You are going to see the problem like this in your lab as well, right? That's why I'm going step by step to tell you how we change our assumptions and how it affects our final equation. Make sense, all of you?
Yes, Professor. Could you go down to the slide of the ICE table, please?
So I'll put it here. I'll put this question mark.
Professor, could you go up for like the one that says the table?
Mhm. So this is where we are going to work. Okay, guys, we will stop here for the day. I need to rush for my next class. And guys, come prepared with the thermodynamics as well in the next class. Keep in
Professor,
mind.
you marked me absent and I'm here.
And you are?
Naila Ramirez.
Okay, give me a second. Okay, I just marked you present. Okay, guys, so see you guys on next Tuesday.